Hi guys, so here we are in chapter 4 where we are going to study about forces and Newton's laws of motion. Um, until chapter 3, which where you studied one and two dimensional motions, you have already studied about displacement, velocities, um, accelerations, right? And you also could understand and analyze motion which are has different accelerations with it, right? So for example, you could solve problems where you have like uniform acceleration or constant acceleration, where you used three equations of kinematics, right? Involving initial velocity, final velocity, accelerations, all that sort of stuff. You also learned about uniform motion in general, okay? So be sure to distinguish between constant acceleration motion. Sometimes it is also called uniform accelerated motion, and distinguish between this and uniform motion in general. And uniform motion means there is no acceleration at all. So uniform motion means velocity constant. Uniform acceleration or accelerated motion means acceleration is constant. And in this chapter, we are going to learn about what causes the acceleration, okay? So the reason for which accelerations are caused, the reason for which you are seeing an object either speeding up or slowing down, okay, is the topic of this chapter. And then, of course, we are going to add a few tools to our toolbox analyzing motion. So again, we are thinking about like, what kind of activities keep an object in motion, or what kind of activities stop an object when it is already moving. And it seems like you would, based on experience, you would keep pushing an object in order to keep it in motion. It also feels like you would not have to apply any force to stop an object from moving. Now, both of these two experience, or anecdotal experience, I should say, are not necessarily true in every reference frame. It only works, these kind of things only works when you have a frictional surface, okay? So for example, if you roll a ball on a rough surface, like in a field, right? Or in general, on a road, if you have a perfectly flat road and if you roll a ball, or if you just roll a paper, for example, right, for a few inches or a few feet, depending on how hard you were throwing it, it will stop eventually because the friction stops it. Imagine if there was no frictional force. What would happen is that it will keep moving with constant velocity, whatever velocity you have given it. On the other hand, if you have an object at rest, it would stay in rest. It would not move, no matter how frictionless your surface is, if you don't do something from outside. So these kind of experiences, they will basically shape our theoretical basis, foundations for this chapter, which we call basically Newton's laws, or three laws of the Newton. So let's go on. What causes motion? The sled is moving but will slow with friction. The more friction, the faster it slows. In the absence of friction, if the sled is moving, it will stay in motion. And this is not something we see every day. The reason behind is you don't see real life surfaces most often, or most frequently, that are frictionless, but you do see some of them, or at least nearly frictionless. For example, one example could be the bowling alley, right? So if you go to bowling, and then if you can see that the ball that's rolling down the lane is not stopping very, like, it's not likely to stop by friction. It's not that there is no friction, there is friction, but it's a very low friction surface. Pool tables or billiard tables are basically also examples of that. But again, these are not frictionless. You can simulate frictionless surfaces, almost frictionless surfaces, let's say, in a laboratory. And if you do that, you will going to see that if you move an object in a frictionless surface, then it will not stop automatically unless you do something from outside, unless there's either a friction or something from outside that stops it. All right, so if the sled is moving, it will stay in motion. Newton's first law basically tells you if you have an object that is moving, it will keep moving until an external force or external something tries to stop it. It also says that if an object is at rest, right, it will not start moving until you do something to it or an external entity does something to it. And we call both of these two entities or these two activities as like application of force. Okay, so force is something which will cause motion. Force is something which will also stop motion. There are different kinds of forces, and in this chapter we're going to catalog them or list them. Okay, so there is a push or a pull. There is, and every force has agent. Okay, so the first two forces that we are talking about is either push or a pull. And you can see that they both can basically be applied to move an object, right? Move an object or put an object into motion. Sometimes it can also be used to stop an object. So for example, a push can be used to either move this punching bag away from you, or you could also use push to stop it from hitting you, right? So you can apply the force or push force in both, for both purposes. Now, every force has an agent. And every time you are thinking about what is an agent of force, you should think about what is causing the force. And in most cases, you will see that there is a certain entity that is in contact with the force. For example, if somebody is throwing a ball, making a pass, this football player is making a pass, right? And then if you think about the agent, you could broadly say that this person is the agent. But if you want to be very precise, very particular or accurate about what is the agent, you are going to say the hand of the football player is the agent. The reason behind is that this is the part of the body which is directly in contact with the ball. And we're going to see that not every force needs contact or physical contact, but it's easy, and you will see in later problems that if you have an agent and if you have an object that is moving, the force has to be applied directly with the physical contact for some forces. So in this cases, it's an easy answer. If you want to know what is the agent, just see who is holding it, but then what is also holding it. The hand is holding the ball. So that's why the agent is the hand. Similarly, if you think about this baseball bat and the ball, right? So the agent here is the baseball bat. Okay. Now there are long-range forces as well, as I was saying, like not all forces will need physical contacts, okay? So for example, long-range forces like gravity, they don't need physical contacts, but it still applies, it still has an agent. In that case, it's an easy answer, because if you have a gravitational field, if you know that Earth is pulling an object down because of the gravitational field, you are going to say that Earth is the agent, okay? Now, force is a vector quantity. By now you have probably guessed, because you can see that every time you're applying a force, you are applying it in a certain direction, right? So as long as, so it must have two different parameters to it. It just like any vector quantities, you must you must specify how large is the force, you must specify how strong is the force by a number, and then you must specify in which direction it is working. So we are going to work with forces just like any vector quantities: velocity, accelerations, displacement. And as I was saying, you will always draw a force and as an arrow, right? And just like any vector quantities, the arrow length or length of the arrow is basically going to tell you how large is the force. So the length of the arrow is proportional to the magnitude of the force, okay? So if this is like 50 Newton of force, then you can basically think of a scale. Each of these scale or marker is basically going to give you 10 Newtons. What I'm trying to say here is that, let's note it. And what I'm trying to say here is that you can arbitrarily generate a length scale, okay? And they don't have to be like as accurate. You could see probably not all of these lengths are similar, but I'm roughly making each of this. This is a horrible drawing. Let me write it again. I'm basically trying to say each of these segments are 10 Newtons, and the whole thing basically is 50 Newtons if you can, if you have actually specified a length scale, okay? So this 10 Newton is equivalent to whatever length I'm choosing for it. And accordingly, you are going to draw force vectors, just like acceleration vectors or velocity vectors. You do the same thing, you just attach a particular unit to it, okay? In this case, the unit is Newtons, as we are going to see later. The second rule that you need to know is that you are always going to put the tail of the force at the object, wherever the object is. Remember, we're still with the particle model, okay? So you have put a particle, and then you are going to draw a length vector or the force vector, and that force vector is basically going to show you in which direction this particle is feeling the force. Because of the application of the force, depending on other scenarios or other constants or situations, this object is going to probably accelerate along this line. That's what we're going to see. Okay. Then, yeah, there are like several different examples of force vectors, right? So there are different kind of force vectors. We are continuing our cataloging. We can have tension, spring force, and weight. These are the three very, very important forces that you are going to see eventually in a lot of problems that you are going to solve with forces. And this is basically, the first one is the tension, okay? So you have an object, you have attached a rope with it, and somebody is pulling the rope. Now, if you think about the forces, there are two different kinds of forces, right? One is this person pulling the rope. So there is one agent, the hand, that is pulling or applying the force to the rope. But if we are interested about the object, not the rope itself, if we are interested about the object, then the agent must be the rope, right? So there are two forces, and this is a force of tension. And the tension force is always to which direction the rope is being pulled, okay? So for example, here, the pulling force is from left to right. If you had, instead of a person, if you had a pillar and the rope was tied to it, it would still be from left to right. Okay, the spring force, for the spring force, it's also very interesting. This is a different kind of force. It is kind of a reactionary force, okay? So because there was no force at all initially if there is no compression or stretching. So imagine if you have a spring, if you have a box attached to it or a block attached to it, and if you are compressing it, what will happen? If you apply a force, initially if you apply a force and you compress it, after a while or whenever you want to release it, the spring is going to apply a force on the block in the opposite direction. We call this force as spring force, not the first one, okay? So this is not the spring force. This is the spring force, which is basically going from left to right. So this is why we have defined it such way. The reason behind it is that the spring force is caused by the spring. For the spring force, spring is the agent. For this force, which we just canceled or which we just disregarded, that was the force which was coming from the hand. Okay, somebody was pushing it, right? So for that, the agent was the hand of the person, not the spring. If we want to talk about spring force, we always should talk about the force that is applied by the spring, not somebody else. Finally, we have weight, right? Weight is basically a force by which earth pulls an object towards its center. So it's basically, if you want to think of an object, if this is earth, and if you have an object sitting on top of it, okay, then you could simply draw a vector towards the center of earth, and that's the weight. It's basically a force which has a special name, and we call it weight. Eventually, we're going to see the formula for it, but for now, the symbol, you need to remember the symbols. Weight is W, spring force is F sub SP, and the tension is uppercase T. All right, moving forward, we have now superposition of forces. Okay, so what happens if you have multiple forces working on the same object? And this is going to happen all the time in your problems. If you are going to see many forces or multiple forces acting on the same object. So here's an example where you have one object being pulled in this direction. So you have one force in that direction. Let's say this is F1. You have another force being pulled down, right? We can say this is F2. We can, if we want to know actually what is the summation, what is the resultant, what is the cumulative effect of application of these two forces simultaneously, we will have to find the resultant. Remember how we did vector summing in chapter 2 or chapter 3 actually, right? So this is the same thing, right? You have F1, you have F2. If you want to find the resultant, you have to complete the parallelogram, right? Remember the parallelogram diagonal gives us the resultant. So F net is F1 plus F2. Similarly, if you have multiple such forces, without even drawing them, you can simply just write as algebraic sum of these forces or vector sum of these forces, okay? So they're the same thing, because if you are in one dimension, that's the signs are going to give you the correct summations or summation result. If you are working with vectors, you can still do this, but for generally speaking, if you know the components, that works best. If you don't know the components, you have to resort to like the parallelogram laws, and then you can only, you're limited to only working with like two vectors at a time. So at first you are going to do F1 plus F2, find whatever it is, F net is, and then you add F net with F3, and then with F4, and then with F5, like one at a time. So this is a tedious method. We will definitely go with the components if we have to ever do this. But the net force is basically the force which can like take away, we can basically just replace all the forces, okay? So when you have drawn this red arrow, you don't need to draw these two guys anymore in a problem. So remember, many times you're going to use the net force and you're going to form equations on the basis of net force. So this is a very important, important concept to understand. I strongly recommend you guys to read the discussion and description of the net force or vector summation of forces from the textbook as well. All right, so Again, this is, we already know, this is gravitational pull or the weight. You have already seen the acceleration, which is minus g. Remember, if you take the y-axis to be along the, going up, right? If this is your y-axis, then you have seen g or minus g as your acceleration along y-axis for a free fall motion. This has something to do with the weight. Eventually, we're going to see that weight is basically going down. So this is mass times acceleration due to gravity. And we're going to probably see free fall or gravitational pulls in our experiments at some point. Anyway, it's always vertically downward. That's the whole point of this slide. Spring force, as I already said, that the spring force is from left to right, because when you are compressing, it is left to right. When you are stretching, remember, you could also pull the object from left to right, and that would be done by yourself, right? That's like your hand is the agent for that. But once you stretch it, if you leave it there, if you now let it go, what will happen is the spring will cause a force, the spring force, and that will basically bring it back to its original position. So if you stretch it, it will come back. If you compress it, it will also come back. And notice that these two forces are opposite to each other. So spring force do not have a constant direction. It doesn't always apply to the same direction. Unlike the gravitational force, right? No matter where you go, the gravitational pull is always downward, straight vertically downward. But for spring force, that's not the case. It changes depending on what kind of action has caused it, right? So if you stretch it, it will come back. It will go from right to left. If you compress it, it is going to go from left to right. Then you have tension, and you have different kind of tensions. This is also like another tension, just like previous one, but this time you have the tension force working with an angle, okay, with the x-axis. So remember what we did with any vector working with angles, right? We always worked with the x and y components, and that's exactly what we are going to do here. When we are going to solve a problem where a force is being applied in an angle, we are going to take the x and y components, and we are going to treat these two x and y components or x and y motions independently or separately, all right? Anyway, as previously said, it's always in the direction of the string or rope. Finally, normal force. Actually, we have a couple more to catalog after this, but this is a force which we don't actually like put a lot of significance to it when we are solving usual problems where there is no friction involved. However, every time you are solving a problem involving friction, and for now, from like very soon, we're going to solve problems where we are not going to ignore friction, right? And your answers will be like more accurate to the real life scenarios. So far, you have been neglecting those. Anyway, so whenever there is friction involved, you're going to learn about normal forces, or you will consider normal forces. Where from it comes? It basically is a reaction force whenever you put an object, whenever an object is resting or putting some weight on another surface, right? So for example, this textbook is sitting on the table. By sitting on the table, it's applying, basically, it's pushing down, right? Because of the gravity, because of the weight of the book. And that, for that force, right, the agent is, I mean, the gravity pulls the book, so the agent is earth for that. However, the application of the force on the table, that for that force, the agent is the textbook here. So it's a push force. and the agent is the textbook for that. But if we are not, if we don't consider, or if we are not like focusing on the textbook, applying the force on table, instead, we want to see like what is the textbook is going to do, right? Then we will learn about the normal force, because no object wants to be wants to change its shape from external factors, right? So I will give you an example. This is a pen, or let's say even better examples. This is my cell phone, right? This is a solid object. What happens if you apply a push force from both sides? Does it like readily break? It does not. Of course, at some point, with some application of force, it will break. Like any object, if you are trying to change shape of an object, and if you apply force to it, it will resist until some point, right? Why does it resist? In order to understand that, we will have to understand the structure of solids, okay? Every solid, if you want to focus microscopically to it, you may actually like imagine it to be made of lots of atoms or particles and connected by bonds, and these bonds behave like springs. Remember, we just talked about spring force. This springs, the forces between any two particles or atoms in solids, they behave very similar to the spring forces or springs. And so basically you can think of this structure to be balls connected by springs. What happens when such a network is pushed from outside? It will definitely, just like a spring force, it is definitely going to react to it, right? Just like the spring force, it is going to, whenever it is compressed, it's going to push back and bring back the whole thing to the original shape. Okay, so it is going to resist. So this resisting force or resistance force from the molecules or atoms of the table is the normal force. And on every solid surface, you're going to see this. It is always normal to the surface. So it is always perpendicular to the surface of the table. Okay. If you have, for example, an inclined plane like this, your force will be perpendicular to this. So in this direction. If you have a surface like that, your force will be, let me draw, the force will be something like this. Okay, the normal force, I mean. So the normal force is always perpendicular to the surface, and that's why it's called normal. All right, and it will play a very crucial role in problems involving frictions. So here are normal force examples. I already drew lines like this, so I don't have to say this again. And how solid it is, I mean, you know, the normal force will be greater and greater if you have a more rigid surface. Unfortunately, if you have liquids or gases, you don't have a normal force. So if you have a water surface and if you drop something on the water, you're not going to get a normal force because it's not going to rest there. Anyway, friction, like the normal force, is exerted by a surface. The frictional force is always parallel to the surface. So remember previously what we learned was the normal force is always perpendicular to the surface. And now we are learning about a new force, which is friction, and that is parallel to the surface, right? Which is very easy to understand. Imagine if an object is moving on the surface from left to right, the friction is going to stop it, right? So that's why it is coming from right to left. And if it was originally going from right to left, the frictional force will change its direction, and now it will just simply go from left to right. So frictional force is also not a constant force, just like a spring force. It is going to change its direction according to whatever way the object is moving. So here are examples. You can see the sled is moving to the right, but it is slowing down. It is slowing down because there is a kinetic friction. We call this kinetic friction because it is applicable to an object that is moving. Motion is basically has a um, anything that is moving that has that should have a suffix, the parameter should have a suffix as k. On the other hand, if you have an object that is at rest, you can still have friction, right? This is the reason if you have a solid heavy object on floor, you can't move it very easily without application of force, without application of a huge force. You can't probably move a heavy object. Think about a refrigerator on the ground or on a wooden floor, right? It doesn't, if it doesn't have wheels, then it doesn't move at all unless like really pushed around. So that's why you still have a frictional force and it's working still against the direction of the motion. But unlike the kinetic friction, this is a static friction, and that's why the S stands for static. This applies to only objects. This applies to only objects which are at rest. Drag, finally, I think we have drag and then thrust and then electric and magnetic forces. That will end it. So drag is basically a resistive force of a fluid like air or water. If you let an object move through air or water, you are going to see a drag force coming into play. We are generally ignoring drag. When we are working with free fall, we have not considered drag, but at some point we're going to consider drag and solve a few problems to understand how it works. Now, remember, the drag will forces more and more if your initial speed or whatever speed with which you're moving is larger, okay? So imagine an object was initially here, right? This leaf was initially here, and then it started moving, of course. So when it was here, it was at 0 velocity. When it was here, it had a slightly more velocity. Here it had slightly more. Here it is even more. And now it is right here. So as the velocity increases, and we know that the velocity increases for a free fall, right? Because V final equals to V initial plus A y, which is basically G, and times T. And if you put your origin here, then your velocity and your acceleration are both in the same direction. So that's why it's going to speed up. But as soon as it speeds up, or as long as it speeds up, it is also going to get more and more drag, because drag is proportional to velocity or speed, okay? So as speed increases, drag force also increases. So we are not going to consider drag force until we are like explicitly asked, okay? And then you'll know like when to do this. These are very easy problems, but sometimes you will ignore, most of the times you're going to ignore it in this course. Thrust, it's basically rocket propulsion. This is very easy. So if you have like an exhaust gases that's coming out of it, right? So this is the thrust force is basically the reaction force, okay? So if the gases are going out in this direction, then the reaction force will basically push the rocket up, and thrust, most of the time, thrust works like this: rocket propulsion or rocket launching, jet plane kind of problems. Electricity and magnetisms are like mostly reserved for our chapters in 162 discussions. So we are not going to go into details, but these are long range forces, okay? And like gravity, they are also long range forces. They act on charged particles, and they do lots of like very interesting physics. If you have like an entire semester studying electrostatics, electrodynamics, and or current electricity and magnetism. So I'm not going to go into details. So when we are solving force problems, our first thing that we need to learn is identification or identifying forces, okay? So a typical physics problem describes an object that is being pushed or pulled in various directions. And these push or pull forces are basically going to be manifested in different ways, right? They could be, excuse me, tension, gravity, there could be spring force, sometimes a spring launcher, right? A spring force can push an object, and you can now just think about the motion of an object because the force is going to cause some change of velocities, okay? So there will be, we are going to basically catalog the forces in each of the problems that you solve, okay? So just like in given section where you tabulate what are the given information to you, you are going to write down this is the force, there is a thrust force, or there is a tension, there's a spring force, and you are going to use the correct notation. So look at this table very carefully and stay with this convention when you are solving problems. So you need to apply, or you need to use the same symbols over and over, because otherwise you will confuse yourself and me as well, okay? So we will stay with these conventions for different catalogs, different kind of forces that you have just learned. Once we do this, we should be able to start our discussion on what forces actually do, and that basically will take us to the Newton's laws part of it, and that's the second segment of lecture videos that I'm making from chapter 4. Okay, so I'm going to stop here, and we will meet again in the second segment where we are going to complete the rest of the slides for chapter 4. So until next time, goodbye.